website. So I'm a theoretical physicist, and I work on and like to think about things like black holes and quantum mechanics, fun things like that, or at least things that I find fun. So it really is my pleasure to get to talk today about Einstein's theory of relativity. It's something that's fascinated me ever since I was in high school. Now, Einstein's theory, and Einstein himself has taught us a lot over the last 100 years or so. We've learned about black holes, objects out in space that are so massive, so dense, that if you get too close, there really is no escape, not even for light itself. We've also learned that the universe is expanding, and around about 13 billion years ago, it appeared to come from some sort of Big Bang. Other consequences of relativity or Einstein's theory include the twin paradox, which you may have heard of. If you've seen the film Interstellar, they have a nice visualization of it where some of the crew members fly away and leave one of their crew on a spaceship. They travel off for an hour only to return to find that he's aged around 20 years, while they've only experienced 1 hour time. And this difference in experience of time is a consequence of Einstein's theory. More down to earth relevance, we have a GPS, the kind of GPS that's working all the time in your phone to work out where you are. To have that working, we need to have an understanding of Einstein's theory. Since this is Ireland Maths Week, I really should talk about some mathematics. The problem is that a lot of Einstein's theory of relativity, the mathematics is quite complicated. But fortunately, the twin paradox that I mentioned, we can get a handle on it with some simple tweaks to some quite elementary mathematics, namely Pythagoras theorem. And so that's what I'll be working towards today. First of all, though, when I say relativity, what do I mean? So in physics, often we are thinking about the motion of objects. So say a football, we look at how the football moves, we chart its position in space as a function of time, and we write down equations to predict where it will go next or how it will interact with, say, the air or someone's foot. And as we got better at physics over the years, we were able to write down equations and predict the motions of much smaller things like atoms, or even smaller fundamental particles like electrons. As well as inanimate objects, we can also chart the positions and write down equations for other people, other observers like ourselves. And as they're moving along, they will be able to chart the positions of, say, that football. And what they will see could potentially be different to us because they are moving relative to us. And so when we think about relativity, there are really two main points that summarize what we're thinking about. So from this different reference frame of this guy here on the bus, or this different perspective, what things look different? So in this example, say the football, its motion looks different. But we also want to know what things look the same, if there's anything that's invariant from this different perspective. There's a nice analogy in some elementary maths. If I just take the XY grid here, and I think about this point at coordinates 4, 3, that means it's 4 in the X and it's 3 in the Y direction. And I draw this blue line here. If I asked you, what is the length of this line? How would you go about calculating that? Well, if you remember high school maths, or if you're still in high school doing this maths, then you might draw something like this. A here is the distance in the X direction, so 4. And B is the distance in the Y direction, 3. And then I've just labeled the length that I want to calculate as C. And with these 3 labels, some bells might be ringing in your head, given the title of this talk. And here's Pythagoras to tell us his famous theorem, a squared plus b squared is c squared. And so we can invert this for c like this by taking a square root. And if we plug in the numbers for a and b, we'll find that we'll get the length as coming out as 5, which is the correct answer. And so Pythagoras is a happy guy. Now imagine putting a different grid on top, just rotated slightly. So this red grid now, because I've rotated it, the red coordinates will be different than the original coordinates. Here, the x coordinate is greater than 4 now, and the y coordinate is less than 3. If I said, let's calculate the length in this case, you might just jump straight to the answer. You might say, well, I don't need to even calculate it. I know already from the previous grid that the length was 5, and we haven't changed the length of this line. We've just added another rotated red grid on top. But then you might think, well, what if I did try to use Pythagoras' theorem? But now we've got different numbers. A here, the length along this red x direction is greater than 4, and B, the length along the red y direction is less than 3. So will I get the same answer? And actually, it turns out that you do get the same answer, even though A and B are now different. And this connects up with those 2 points of relativity that I said at the beginning. Namely, the thing that's different, or what's different, are the coordinates in the two different grids, in the two different coordinate grids, the coordinates of that black dot. What's the same? Well, the length, as long as we're calculating it using Pythagoras, the length is the same in either coordinate grid. And I should say that while that was just an analogy, we'll actually see at the end that that really is what's happening in relativity. To get to some proper relativity, I need to introduce a crucial concept of space-time diagrams. Now that's where you, instead of drawing just spatial directions, one of the directions is replaced by a time direction. To explain what I mean by that, I'm going to go through a little scenario. Imagine some really, really long ruler on the ground. And let's say we've got units of meters there at the side. Imagine some blue guy standing right in the middle. And there's a rock off to the right there. The blue guy's about to throw a red ball, and this dog is going to be running around. So let's watch that animation. So the dog there ran off to the left and came back, and the ball just went off to the right. Now I'm going to play that animation again, but as I'm doing that, I'm going to slowly drag the whole setup up the screen and chart the positions of all the objects as I do that. So you see here, these blue, red, gray, and sort of beige lines are appearing to show us the motion of the different objects. And now if I place a grid on top of all those lines, we have our first space-time diagram. So you see the x-axis now is space, and these vertical dotted lines represent the different notches on our long ruler. This is 1 meter. This is 1 meter off to the right from the blue guy. This is 1 meter off to the left. This is 2 meters off to the right, and so on. But now the vertical axis, as we dragged the picture up, is now time, measured here in seconds. The rock, which is completely stationary relative to the blue guy, doesn't move left to right in this diagram. Its position, its x position, doesn't change in time. Hence, its line is just going vertically up. The red ball moves off to the right, and so its line is slanted away from the vertical, going off to the right. And the dog, because it runs away to the left initially, its line is slanted off to the left, but because it turns around, its line slants back off to the right. Now, this whole grid was set up relative to the blue guy. The spatial direction is about distances relative to them. And so because this grid was set up with respect to the blue guy, we say this is the blue guy's reference frame, or just the blue frame for short. Now imagine we've got our blue frame, or our blue guy, and some red guy flies past, going off to the right, with their own ruler set up. For the red guy, he would, as he flew past to the right, he would then see the blue guy moving relatively to the left of him. Now, given we've both red and blue guys have their own ruler setups, we can equally well just form their own independent reference frames that are built relative to them. So here we've got the blue frame on the left, where the blue guy is always on the vertical line. And then we've got the red frame on the right, where the red guy is always on the vertical line. And the little vertical dotted lines in the red frame represent the notches on the red guy's ruler. We can think about how the red guy now looks in the blue guy's frame. Here he is, moving off to the right, just like the red ball. We can think about the blue guy moving in the red guy's frame. Because he was moving to the left relative to the red guy, his line will be slanted off from the vertical to the left. I should have said as well, it's important that the faster you go, the more your line will be slanted away from the vertical. Maybe this is obvious for some of you, but if I'm covering more distance in the same time, then my line will be slanted off further away from the vertical. Now, in terms of relativity, and we want to understand what things look different from these different perspectives, how that manifests here is we want to know what the rest of this blue grid, these blue dotted lines, look like in the red grid. And vice versa, we want to know what the red grid looks like inside the blue grid. And your first guess might look something like this. Ignore the slight change in animations there, that's just my lack of animation skills. So here's the blue grid, because the blue line is vertical, and here's the red guy flying off to the right. And I've just drawn all the other red dotted lines, the notches that the lines that represent the notches on the red guy's meter stick, moving off with the same slant off to the right, because they're also traveling off to the right at the same speed relative to the blue guy. And similarly, I can just draw the red guy's frame. Here it's the red guy's frame because he's vertical. And then the blue guy's moving off to the left, as are all the blue dotted lines. His grid is slanted off to the left. And then we can think about, it's useful to think about this, a nice transformation, a smooth one that goes between the red grid and the blue grid. And all that's happening here is we're just shifting over these horizontal lines to transform from one grid, the red one, to the blue one and back. We can also imagine other objects in this whole scenario as well. Here's a green ball that I'm going to have the blue guy throw off to the right at twice the speed of the red guy. From the red guy's perspective, he'll see the blue guy going off to the left and the ball going off to the right, but it won't be going quite as fast for him. This is exactly like everyday experience. If I throw a ball at 10 miles an hour and you run past me in the same direction at 5 miles an hour, then you'll see that ball traveling away from you only at 5 miles an hour. In terms of these space-time diagrams, this is the sort of setup we have. We have this blue, this is in the blue frame now. The red guy's moving off to the right, and the green ball here is moving off at this faster speed, so it's angled further away from the vertical. If I transform to the red frame, now the blue guy's going off to the left, and the ball is closer up to the vertical now because it's going slower. In terms of that smooth transformation I showed you before, if I just shift over the horizontal lines I can get from the blue, the red frame, and as I do that, you can see that the speed of the ball decreases. And this is exactly as I was saying, everyday experience. This is what you experience, sorry, in everyday. The problem is that this picture that agrees with everyday experience is not quite correct. It breaks down if we're going too fast. It's only approximately true for slow speeds. And the first person to realize this was Albert Einstein, just over 100 years ago. And the way he figured it out was as follows. He was thinking about the Scottish physicist, James Clerk Maxwell, who just before Einstein had figured out the laws governing electricity and magnetism, or together, electromagnetism. And from those laws, he realized that light itself is just a wave of electric and magnetic energy, of electromagnetic energy. And that wave propagates at some constant speed, which we now just call the speed of light. And Einstein thought, well, in this theory that Maxwell came up with, that works well with experiments, you could imagine having a lab where you have electric and magnetic fields that accelerate charged particles like electrons. And as you do that, you can just predict and see from Maxwell's theory that those accelerating particles will emit light. They'll emit electromagnetic radiation, and it will propagate out at this constant speed of light. And Einstein then realized that from Maxwell's theories, it actually doesn't matter how fast the lab itself is moving. The light will always propagate out from these charged particles at the same speed. The lab could be sitting on the ground and the light would radiate out of the charged particles at the speed of light, or the whole lab itself could be on a train moving at 100 miles an hour, and you'd still see the light getting emitted at this constant speed of light. And so from that, he had one of his best ideas. He had a lot of great ideas. But this idea was that the speed of light must be the same in every reference frame. And this actually contradicts that everyday experience picture I showed you before. To see how it contradicts this picture, we have to change our setup just slightly. Before, the x-axis was measured in meters, but this is a little small for our purposes now. So instead, I'm going to measure the x-axis in units of roughly 300 million meters. So that means that this first notch here represents 300 million meters to the right of the blue guy. The second notch represents roughly 600 million meters, and so on. And why have I chose this number? Well, it's the distance that light travels in a second. So it's a light second, or just LS for short. And this is useful for our picture because then if you imagine the blue guy at the very beginning just flashing a torch, that light pulse will travel off in a diagonal line in our space-time diagram. That's because it travels exactly 1 light second to the right for every second. Okay, so now we go back to our scenario with the blue guy and the red guy flying past, but let's add some fixed mirrors on either end of our rulers, And we're going to flash 2 pulses of light. They're going to fly out and bounce off the mirrors and come back to us, and then we'll see them at the end. In terms of a space-time diagram, for the blue guy, this is what we have. The light will fly out in either direction, and at some point it will they'll hit both the 2 mirrors on either side, and then it will bounce back and eventually reach us again. So we get this diamond shape in the space-time diagram. If we add in the picture of the red guy now, here the red guy's moving off to the right, and then I'm going to do the transformation to the red guy's frame that we had before, where we just shift over the horizontal lines. The transformation that agrees with everyday experience. And you can see just by doing that, all the lines, the yellow lines, just like the green line from the ball before, have shifted over. The one on the bottom right here is shifted up closer to the vertical. But that means that from the red guy's perspective, this bottom right yellow line is going slower than the speed of light. The speed of light now in our picture is a diagonal line, but this line is not diagonal. It's closer to the vertical and is hence going slower. In a similar way, you can reason that this line on the bottom left is further away from the vertical than the diagonal. And so from the red guy's perspective, we'll be going faster than the speed of light. And this line will be going faster, and this line will be going slower. So by doing this everyday experience transformation of shifting across the lines, we see that these light rays actually look like they're traveling at different speeds to the red guy. And so that contradicts this idea that comes from experiments, really, that the speed of light should be the same in every reference frame. So how do we resolve this? How can we transform from this blue frame to the red frame while keeping all the diagonal lines diagonal, keeping them going at the speed of light? Well, let's think about it less like a physics problem, more like a geometry problem in maths. Forget about the physics for a moment and we'll come back to that. We can imagine squishing in a diagonal direction from top right to bottom left, exactly like this. In doing so, we can see that the red line kind of looks like it's coming across to the vertical. We could also imagine stretching from the top left to the bottom right, like this. And as you do that, the red line seems to also come across to the vertical. So what about some combination of the two? We could stretch in one way and squish in the other. Just like this, to get into the red frame, because now we have the red line going exactly vertically up. So this is our new red frame. And because we were just squishing diagonally and stretching diagonally, we don't change any diagonal lines. They stay diagonal. And so to the red guy now, these light lines will be still traveling at the same constant speed. So we found our transformation. And if we do it exactly in reverse, if we squish in the way that we stretched and we stretch in the way that we squished, we'll get back to where we started. This transformation has a name, named after the mathematician who came up with it, a lorentz boost. I think the word boost comes from the fact that if you imagine being the blue guy and you want to get to the reference frame of the red guy, you really need a rocket to boost you up to that speed. So this transformation does exactly what we want. It takes us from the blue frame to the red frame while keeping the yellow lines diagonal, and so keeping the speed of light the same for everybody. But maybe you were thinking that there might be a problem, because I was arguing before that we had this picture of our everyday experience where we just shift over the horizontal lines. But that looks totally different than this new picture, this new Lorentz boost, which I'm now arguing is really the correct thing. So how doesn't this new picture, this new Lorentz boost, contradict our everyday experience? So if we just focus on this Lorentz boost picture for a second, if we're talking about everyday experiences, we're not normally going at some substantial fraction of the speed of light. So let's draw this picture, but if the red guy was going much slower. If we did that, the picture would look more like this. Another thing to think about is that in everyday experience, we're not normally looking out over and measuring over distances of some number of 300 million meters. So let's just focus on small distances, some strip, just close to the blue guy. So if I just do that and ignore again the lines changing thickness, that's just my bad animation skills again. For more detail, I'm just going to add in some dotted red lines there, and then now all I'm going to do is stretch out this picture so that now we're talking not in terms of light seconds, but in terms of units of meters again, more like our everyday experience. And just from doing that process of looking at the strip and stretching it out for small velocities, it starts to look a lot more like that picture from our everyday experience where we've just shifted over the red grid. And so now we can see that actually, while boosts looked very different before, they do agree with everyday experiences, as long as we're talking about short distances relative to light seconds and speeds that are much shorter, much smaller, sorry, than the speed of light. Now that we're happy we've got internal consistency with our everyday experience, what are some new consequences, some new predictions coming from Einstein's theory? What are some consequences of these boosts? So let's take the blue frame picture again and think about when the light hits those two mirrors. That would be these 2 points here. It happens at the same time in the blue frame, like 2 clicks on either side of you. But if we transform to the red guy's frame, then it looks like the light hits the right mirror first and then the left mirror after. It doesn't happen anymore at the same time. This is totally different than what would have happened in the everyday experience picture I showed you before. And so we get our first lesson from relativity, that there is no concept of absolute simultaneity. That means that events that seem simultaneous for one person may not be simultaneous for someone else moving relative to them. So for example, if people were tuning into this talk in Ireland and in New Zealand, say at 6 p.m. Irish time, you would say, oh, they're tuning in at the same time. They're tuning in simultaneously. But actually, some alien spaceship flying by the Earth at thousands of kilometers per hour would see them tuning in at different times. The second lesson, if we now take that blue frame again and focus on this point here along the red guy's trajectory. In terms of the coordinates coming from the blue frame, these blue x and t coordinates, it's 2 in the x, so that means 2 light seconds, and it's 4 seconds in time. So for the blue guy, this dot is happening at 4 seconds after he started this clock. But what's the time for the red guy? Well, to figure this out, we can transform to the red frame, and here's the dot in the red frame. And now if we just count up from the bottom of the red guy's frame, we can see there's 1 notch, 2 notch, 3 notches, and then just a little bit. So the coordinates of this point, well, it's 0 in the x, because it's on the red guy's path. This point is no meters, 0 meters from the red guy. And it's approximately, just from looking at the picture, about 3.5 seconds up for the red guy. We could have even seen this from the blue frame, actually. If you just look at the red dotted lines and we just count up from the sort of middle one, we get 1, 2, 3, and a little bit. So it looks like the time for the red guy here is less than 4 seconds, but the time of this point was 4 seconds for the blue guy. So this is our second lesson from relativity, that the time experienced by different objects or different people can be different depending on their relative motion. And this is an entirely new concept, and one that's quite hard to accept when you first see it. So I said the time for the red guy was around about 3.5 seconds. But how would you actually calculate this time? So we're in the blue frame, so we have our blue coordinates, x and t of this point. That means that it's t up and x across. And as I said before, that's t was 4 seconds and x was 2 light seconds. If I just shift across this t now to make this look more like a triangle, remember that what we're trying to calculate is the time experienced by the red guy, which is this, I'm going to denote here by this capital red T. Then, because we've got this triangle, bells might be ringing again and you think, ah, well, it's Pythagoras, right? But actually what Einstein figured out is that the way we should calculate it is with a minus sign instead. And lo and behold, if you actually go through the calculation of plugging in the numbers for 4 for t and 2 for x, you'll get the correct answer. So it wasn't about 3.5 seconds, it was 3.4641 seconds. And everyone's happy now. This would also work in any other frame. So consider some other setup, a black frame here, in which the blue guy looks like he's moving off to the left, and the red guy looks like he's moving off to the right. And here I've got black coordinates x and t. And I want to calculate this time experienced by the red guy. Even just using these different coordinates, the black x and t coordinates, I'll still get the correct answer for the time experienced. And if I went into the red frame, it would trivially be true that I would get the right time. The coordinates of this point in the red frame, well, it's 0 in x, and the time along this line is by definition the time experienced by the red guy. And so looking at this Pythagoras, this new space-time Pythagoras formula with the minus sign, it would just trivially work out because the little t is actually the time experienced, big T, and x is just 0. And given we have this new space-time Pythagoras formula and we see that it works in any reference frame, we have a nice parallel that we can now draw between space and space-time. In space, we have these two different coordinate grids that were related by some rotation. In space-time, we have these two reference frames, the blue and red ones that were related by a boost. In space, we saw that the coordinates were different for the black point as we moved the rotated coordinate grid. And similarly, in space-time, we saw that when we did a boost transformation, we changed the coordinates changed as well from the blue to the red coordinates. In terms of space, we saw that even though the coordinates were changing, using the Pythagoras formula, we got the same answer for the length. The length was the same in any coordinate grid using the Pythagoras formula. And also in space-time, we saw that the time experienced along the line, what's known technically as the proper time, it was the same regardless of which reference frame we were looking at, as long as we were using this new space-time Pythagoras formula. And this is exactly like the 2 points of relativity that I mentioned at the beginning. The coordinates are the things that change from different reference frames, but the length in space, or the proper time here in space-time, those are the things that stay the same. Bonus points. 1. If I'm in the red frame, like this here, the red line is vertical, and I look at this point off to the right, so 3 light seconds off to the right, and I boost into the blue guy's frame, I would get this point here, and it would have some potentially different blue coordinates now, x and t. And x is going to be, if you just look at this picture, you can see going across, it's greater than 3 light seconds for the blue guy. And if I was to try and calculate the length of this line, well, I know over here that it was 3 light seconds. How do I get the length in this new picture? Well, it's space-time Pythagoras formula again. But if you're looking closely, you'll see that this actually looks different to what I had before. When I was calculating the time experienced by the red guy, I had a positive sign for the t, whereas here I've got a positive sign for the x. So what's happening here is, in summary, if you want to calculate the time experienced along the line, then you should use this Pythagoras formula. If you want to calculate the distance, then you would use this Pythagoras formula. And the dividing line that tells you when you should use which formula is the diagonal, the line that light would take. The second bonus point. So we've always been calculating times and distances from the origin. But what happens if you have 2 points like this and you want to calculate the time experience as you're traveling between them? Well, just like Pythagoras, we don't need to always do things from the origin. We can think about the difference in the x coordinates between these 2 points, delta x, and the difference in the t coordinates, delta t, and plug those into our Pythagoras formula, our space-time Pythagoras formula, to get the time. Now, with that space-time Pythagoras formula, we're now ready to look at the twin paradox. For those who don't know, the twin paradox is this effect that comes from relativity, where one person flies away really, really fast and flies back only to find out that the person they left is much older. Just like in the movie Interstellar. In terms of a space-time diagram, that would look like this in the blue guy's frame. Here the blue guy doesn't move and gets much older, while the red guy flies off to the right and comes back. If we take the coordinates of this red guy and write them as delta x and delta t, that means that this point is delta x light seconds away from the blue guy, and in terms of the time for the blue guy, it's delta t up. Then we can get this nice triangle, and because we're just, for simplicity, saying that this is the same journey going away as it is coming back, we've got the same triangle up at the top. And now we can use our space-time Pythagoras formula to calculate the time that's experienced by the red guy. So that would be this capital red T here, and this is the formula we would have. The 2 in this case is coming from the fact that we have these 2 triangles. Now, if I divide both sides of this equation by 2 delta t, I would get this. Now, this is useful because 2 delta t, if you see from this picture, is just the time that's experienced by the blue guy as the red guy goes off on his round trip. So I'm going to replace that 2 delta t by a capital blue T to represent the time experienced by the blue guy. Then we're just left with delta x over delta t, which, as you probably know, would then be the velocity, change in space over change in time. And in this case, it's the velocity of the red guy as measured by the blue guy. And so because it's the velocity of the red guy, I'm going to write it as a red v. I'm using units of light seconds here for distance. So actually this velocity in these units will just be some fraction of the speed of light. If it's 0, then that means that the red guy is static, not moving relative to the blue guy. If it's 1, it means that he's traveling at the speed of light away from the red guy, away from the blue guy. If it's a half, then that's just half the speed of light. So I wanted to finish off by doing a little calculation to show you how this works. And I thought this was probably the most relevant problem I could think of. How fast would we have to go if we flew away from Earth and came back just like the red guy to make the rest of 2020 only last 1 hour? So we have this formula from the previous page, and our input here is 2.5 months for the blue guy. In this case, the blue guy really just represents everyone else here on Earth having to sit through the next 2.5 months of 2020. The red T is the 1 hour. That's how long we want it to take for us flying away from Earth and coming back. So plugging in those numbers, you get for this ratio, this number here, 0.005. And if you invert the formula above for V, you can find out that V is this huge fraction of the speed of light. It's really, really close to the speed of light. In terms of normal units, that's nearly 300 million meters per second, which is basically the speed of light, but not quite. To put that in a bit more context, at that speed, you would lap around the world, going around the circumference of the world every 0.13 seconds. And while this sounds great, if you could just do that for an hour, that would bypass a lot of time, essentially taking you into the future. The problem is the energy it would require to get you to this enormous speed. I did the calculation for myself at my mass, and what I found was to get me up to this speed, it would take around about 70,000 of the largest atomic bombs we have. That amount of energy, but compacted into a rocket booster strapped onto my back just to get me up to this speed. And while this sounds crazy, and these effects maybe seem a bit counterintuitive, we actually do observe them for particles that are much, much less massive than me. Because these fundamental particles can be so light, we can actually accelerate them to these crazy speeds and really observe these effects of relativity. A couple closing things. I feel like I really only scratched the surface here of Einstein's theory. There's so much more in terms of his theory of general relativity, his theory about gravity. And if you're interested, I would recommend Minute Physics on YouTube. I borrowed a lot from them for this talk. They have some really great videos on relativity. And there's a lot of other nice YouTube channels out there as well I would recommend. So yes, thank you all so much, and all the best for 2020, however long that may be for you.
Thanks, Ian. That was a very nice talk. Can you hear me okay?
Yeah.
Good. Okay. Questions are just starting to come in here now, so I'm just going to encourage people to ask questions there, if you can think of anything. The first question is from C. O'Donnell. Does the maths here suggest that we could travel back in time?
No, unfortunately, no. That would be nice. But yeah, the maths, and if you follow it, go through all the good textbooks and everything, you can see that just as I was calculating there at the end, that the energy that it would take to get me to some enormous speed is enormous, and it grows exponentially. So just to go a bit faster, I'd have to use way more atomic bombs, and the amount of energy it takes to get me to the speed of light is infinite. I could never reach the speed of light, and I have to at least go faster than the speed of light if I'm going to want to start going backwards in time.
Okay. Next question is from Martin Topinka, one of our DIAS colleagues. He's saying, thanks for the talk with the great animations. He says, I have a feeling that you just showed half of the twin paradox, which is actually not the paradox itself yet. So I don't know if you want to clarify.
Yeah, I'm not sure. I think normally the twin paradox is that there is no paradox. This idea of you coming back, it's one of these where they call it a paradox, but really it's not. It just is a real effect. If you fly away fast enough and come back, you will genuinely be, you won't have aged as much as everyone else that you left behind. It seems paradoxical because it's not something that you experience in everyday life, but that's just because you're not going fast enough.
Terry Trevito is complimenting you here on a.
Oh yeah, thanks, Terry.
Ronan Mehigan asks, in the Feynman lectures, he resolves the twin paradox by saying the twin on the rocket knows they're moving as the rocket will have to decelerate or experience a force to return to Earth. Is that correct?
Yeah, that's a really good point. So in some sense, there's nothing to resolve, as I was saying, but the crucial difference, what's the distinction between the two people, the two twins in the example, the one that goes away and the one that comes back. And so I think what Ronan's mentioning there is that the one that goes away has to accelerate in the first place to even start moving away from the one that's on Earth. And they also have to decelerate and turn around and come back. Whereas the person on Earth doesn't have to do anything. And so there really is a physical difference between the two people, and that's what's accounting for the difference in the times that they experience.
Okay, next question is from Christina, and I think actually this was sent privately rather than publicly, by mistake possibly. But does the idea of space, time, and time travel prove that a parallel universe could exist, or that something similar could exist?
I'd say short answer, no, unfortunately. Haven't seen anything like that come up.
Sarah A. Saad is asking, do the people who live on Earth experience different times? So I guess this is about, everyday experience versus...
So, no, unfortunately, like moving around at the speeds that we do, you would never notice it. There's another effect that's slightly different to what I was talking about, not quite the twin paradox, but it comes from Einstein's more general theory of gravity. And it's exactly the thing you have to take into account with GPS. And so that the effect is that if you fly away from a gravitational body, you orbit it at a much higher radius than where you started, your time will seem to tick faster than all the people that you left behind on the surface. And so for people out in the International Space Station, their time is ticking slightly faster than people down on the surface, but it's so minute that you would never notice it. A person could never notice it. But the clocks that we send up into space have to be so accurate to get GPS to work that the clocks would notice it. Things would go out of sync and GPS just would give you the wrong position all the time. So genuinely, when we build clocks here on Earth that we send up into space to do our GPS, we have to start them on Earth running slightly at a slower rate so that when they get up there, they're running now at the same rate as the ones down here on Earth. So that's about as close as I could get to, I can imagine you could get to people experiencing different times here on
Earth. That was the last question. So we can give a little bit more time for people to type in their questions if they want. And just while we're waiting, I might ask a quick one myself. So you mentioned actually about the film Interstellar and them kind of showing some special relativity. And I remember hearing at the time when the film came out that people thought the physics was really well done in that film. And I was wondering if you thought that as well, or if you spotted that there was kind of, often the films kind of take, they're not too careful about being accurate with the physics. So what did you think about that one?
No, I thought for the most part it was really fantastic. As Terry is, I just noticed Terry saying Kip Thorne was the main science advisor on that film. And he had a good team of, say, postgraduates and PhD students helping him out as well. Bar the ending, I won't spoil it, but everything else was really, done properly. The effects of relativity that you see due to the black hole, the way it looks, those were all calculated exactly as they would be in real life, with a small exception, which is this amazing image of the black hole, which I actually had in my second last slide. It looks really nice and light's getting bent around the black hole. But if you were to actually be there, they would, because the black hole itself is spinning, it actually helps spin the light around. And as the light's getting spun around and some of it's coming out and hitting your eyes, the ones that are coming around the side that's spinning towards you will come out at a higher frequency, which for our eyes makes it look bluer. Whereas the light that's coming from the other side that's spinning away from us would end up coming out what's called redshifted, so it would look redder. And actually this effect, because of how fast the black hole is spinning, would be really, really pronounced to the point at which you would barely see any light from either side. The one that's coming out at you that's getting blue shifted would be shifted to such a high frequency that our eyes can't pick it up. Whereas the light that's on the other side, coming from the other side of the black hole, would be so redshifted that it would be down in the infrared or whatever, and we wouldn't be able to see it there either. So this spectacular image of the black hole is completely perfect in terms of physics, apart from they just forgot about frequencies of light on purpose to make it look visually stunning as it does.
Yeah. A few more questions here. So Samantha asks, could it be deduced that time is an illusion if we were to evaluate it from space. So I'm
Oh,
wondering, is this like, you know, when you draw space-time diagrams and you see the line kind of just set in there in a block picture, could it be that time is just an illusion that we experience, but really everything is kind of set into this kind of block of space-time?
yeah, I don't really know how to answer that without jumping outside of my own experience, really. You know, it's nice in terms of physics to describe things in this block picture where we record everything in time in one picture, just like I was doing with the space-time diagrams. You can just draw them on a page. It's there, it's static, but actually it describes, motion. You're just using a spatial direction to describe the motion. But in terms of your actual experiences, at least for me anyway, things seem to be happening in time, one moment to the next. And that is there is a bit of tension actually in modern day physics about the sort of philosophy behind that. It's the difference between the block picture that you mentioned, where you imagine everything is just static and then time is just an illusion, and this kind of more moment to moment picture.
L. Johnson is asking, will the recording be available? And yes, I think it will be available. Do you know where, Ian? Will it be on the DIAS YouTube page?
I imagine so. We'll have to work
Okay.
that one out.
Yeah.
But yeah, it probably will be, from what I've heard.
Okay, a few more questions there now in the last few minutes. Ronan is asking, what are the best approaches at the moment to unify general relativity with quantum mechanics?
That's kind of subjective. I'm sure a lot of different people will say some different things, but from my experience, there's a few different approaches that have nice features, but each of them come with their own bugs, with their own problems. So I couldn't really pick one to tell you which is the best, which approach is doing the best, because for every single one, if they have problems, then they're really not doing the job of actually unifying the theories. But so it depends if these things get worked out. What I would like to see is some of these different approaches coming together and sort of sharing the different ideas that they have, and maybe that sort of a merger will give us something that actually does the job of unifying quantum mechanics with general relativity.
Do you know if the minimum distance, aka Planck length, is independent of the observer? And does it have any implications for general relativity?
Yes, so that the minimum distance is that we normally talk about is to do with when we think that our theories will break down. So I said we can predict things with our equations, predict the motions of things. We can predict a lot about gravity from general relativity, and we can predict a lot about atoms and particles and materials from quantum mechanics. But there are regions and scenarios that we can imagine that really are out there, like at the center of a black hole where matter is collapsing in on itself and getting so dense that our equations that we have really can't be used to predict what's happening there. We just know that they were never designed for that purpose. And so that sort of length scale, the Planck length, comes up in that context. And it's defined as what you would call in relativity a proper length. So that's just like I was saying, how we can calculate the length and that doesn't change from the different reference frames. That would be the same for this Planck length. What we really mean is there's this length that everyone else would agree on. Doesn't matter about your reference frame. If you're calculating using the correct space-time Pythagoras formula.
Terry is asking, how do you feel about the theory of the tesseract? I'm not sure what that is.
I don't know about. Sorry, I don't know about that one.
Okay, I haven't heard about that one either. Thanks for the great explanation and animations, Ian. Any recommendations for a book accessible to the layperson that goes into the maths a bit more?
I'm not sure about a book. I would really recommend the Feynman lectures that were mentioned, actually, but I'm not sure they're quite lay person. Feynman is just in general a great explainer of physics and maths, but I was about to recommend the Roger Penrose book, but if you see that book, you'll probably be put off. It's about a foot tall. No, I would still stick with the YouTube channels nowadays are getting so good, and their animations are, you know, really, really good, and they spend a lot of time thinking about their scripts and getting everything perfect. So I'd say it's a much better medium nowadays to teach you, just give you a layperson explanation of how something works. But then if you want to sit down with a book, then you're probably looking at something that's not a layperson book if you want to really understand how things are working.
Okay, so I think we're into the last two questions now. Sarah is asking about quantum entanglement. So,
oh yeah,
does quantum entanglement somehow allow for faster than light?
That's a really good question, because it's a standard misconception about quantum entanglement that is unfortunately propagated by a lot of physicists. So Einstein was originally disturbed by quantum entanglement, and he thought that things were going faster than light. And he used this to try and disprove quantum mechanics in some way. But actually, eventually people came around and resolved this whole issue by realizing that the thing to talk about that's not going faster than light is information. And there's no causation that can be achieved by quantum entanglement. So things can be entangled, two particles can be entangled and correlated. That means if you see something happen for one, something else will happen for the other. And they kind of work in tandem like this. But you can't use that setup to actually transmit information faster than light. So a nice example or a sort of analogy with that you don't need quantum entanglement to understand is, imagine you're on the moon, or there's two of you on the moon, standing really, really far apart, and I'm looking out at the moon from my window, and I shine a laser on the first person, and then I swiftly move my wrist, and the laser beam tracks across the surface of the moon and then ends up meeting the second person and shining on them. Imagine I move my wrist just fast enough so that the laser beam on the moon, the little dot, the red dot on the moon, moves across the surface faster than the speed of light. You would then be watching this as an observer on the moon, and you would say that beam just went faster than the speed of light. But actually, there hasn't been some sort of physical particles going faster than the speed of light. I'm just firing out little photons, little rays of light from my laser to different points of the moon in some sort of sequence as I move across from one person to the other. And actually, the two people on the moon cannot use this laser setup that I've got to communicate with each other any faster than the speed of light. So while there's something that looks like it's moving faster than the speed of light between them, they can't use it to communicate. And that's really the important thing in terms of quantum entanglement. While things are correlated and there's this effect that seems to be breaking the laws of relativity, you can't use it to communicate faster than light. So this speed limit on communication is still valid.
Martin mentions the twin paradox again, but I think that's kind of similar to what you said before. So I'm going to say that we've kind of dealt with that one. Eric has a question, and this is also going back to something we had before. So it's about unifying theory of relativity and quantum mechanics. But Eric is asking, what's the problem with unifying these two theories?
There's a few problems. One of the simplest problems to talk about is that quantum mechanics is probabilistic, which means that as a theory, you don't get a definite answer out for a lot of things. You get a probability distribution. So when I describe an electron, a fundamental particle with quantum mechanics, I would say, oh, it's got a 90% chance to be here and a 10% chance to be here. I would get some answer out like that, depending on the situation. It doesn't tell me for certain that it's in a particular place. And when I use that mathematics that says 90% here, 10% here, when I actually do an experiment, I would measure it 9 out of 10 times over here and 1 out of 10 times over here. So the mathematics of quantum mechanics is all about giving us probabilities to say where particles will be, roughly speaking. Whereas general relativity, theory of gravity and larger scale objects, is deterministic, which means there's no probabilities. You put in the exact positions of the starting matter, and you'll get out, by using the equations, the exact positions of where they'll be some point later in time. And so but the matter that you put into general relativity, how you describe it is it's not probabilistic. It's got some fixed location where it is. It's got some fixed radius. It's a ball of this size, like a planet or something. So there's just already this difference between the two theories and how they're even expressed mathematically, and trying to merge them as just we've encountered, more and more problems as we've been going along. So the idea now is to, rather than just try and merge them in some ad hoc way, is to come up with some bigger, more unifying theory that takes them both into account, as well as hopefully giving us something new that we can use to make a prediction and test that prediction to show that our new theory really is the next level. It may not be the final theory, it may not be a theory of everything, but hopefully it will unify quantum mechanics and gravity.
Okay, thanks Ian. That's all the questions, and the only other comments coming in are all messages of thanks for your very nice talk. So I think that's essentially a virtual round of applause for your talk.
Great, yes, thank you everyone. It's been fun for me.
Yeah, that's everything from the questions and the comments.
All right, let's close it there.
Okay, thanks Ian.
Great, cheers.